Welcome to another lesson of the course, Curves in Engineering and Architecture. We are in the second part of the course, namely Curves in Road Safety. In Module 5, we speak about three mathematical concepts that serve to solve a problem in road safety. Lesson 5.1 is about differential equations related to transition curves. In previous module, we wanted to design comfortable and safe roads, and we focused on horizontal alignments. The curvature of a curve is the size of the change of tangent direction. In this way, curvature measures how the trajectory bends. On the other hand, it holds that centrifugal acceleration is proportional to curvature, so a jump in the curvature produces a shaking. We then look for transition curves whose curvature varies smoothly from zero, the curvature of a straight line, to some positive and constant value, the inverse of the radius for a circular section. This will produce a smooth variation of centrifugal acceleration that will make drivers feel comfortable. The clothed curve can be a good solution to our problem because at each point of a clothoid, the radius of curvature is inversely proportional to arc length, and the product of both quantities is constant. Denoting this constant by a squared, one gets a family of clothoids of parameter a. But to implement a clothoid curve in the field, the previous equation is not so useful. We rather look for parametric equations giving the coordinates of each point of the curve as functions of the parameter arc length. To get these equations, we're going to use as tools the following mathematical concepts: differential equations, integration, and polynomial approximation. In this lesson 5.1, for each point on a clothoid, we have information about the curvature, and we want to find the position of the point, that is, coordinates. Now, curvature deals with the size of variation of tangent direction with respect to arc length, and the tangent direction deals with the variation of the position. In these two steps, we have info about the change rate of some quantity with respect to another, and we want to recover this original quantity. In other words, we have info about the derivative of a function of one variable codified in an ordinary differential equation, and we want to find the corresponding function as solution of this equation. We will do that in following lesson through the process of integration. To start with it, let's remember the idea of derivative of a function that has been recalled before in part 1 of this course. Imagine you are traveling at that you cover 200 kilometers in 2 hours, that your average velocity is 100 kilometers by hour. If we draw this in a plane, putting time in the horizontal axis and space in the vertical one, then average velocity in the interval 0-2 is the slope of the line joining the 2 points corresponding to 0 and 2 hours respectively. Similarly, the average velocity in the interval AB is the slope of the corresponding second line of the graph of space versus time. In reality, velocity is not constant, and it rather varies with time. So, what is the instantaneous velocity at a given time? An instant of time is a point in the timeline, and we can think about it as an infinitely small interval of time. In this way, instantaneous velocity will be the limit of average velocities when the size of the time interval tends to 0. In other words, instantaneous velocity is the slope of the tangent line to the graph of space versus time, and this slope can be computed as the limit of a slope of a secant line to this graph when the size of interval times tends to 0. In mathematical language, this slope is called the derivative of the function space with respect to the variable time at the time considered. It is simply the instantaneous change rate of space versus time. Now, given some function f of x, the rule assigning to each number a the derivative of a in a defines a new function called the derivative function of f. So the velocity is the derivative of the function space with respect to time, and the acceleration is the derivative of the function velocity with respect to time. Easy examples are a constant function, let's say 5, that has zero derivative because it doesn't change, and the identity function that has derivative function equal to 1 because the graph of the identity is the diagonal line with a slope 1. And for the function x squared, it is easy to see that for every number x, the derivative of f is 2 times x. For example, f prime of 0 is 0 as the tangent line to the graph at the origin is horizontal. Coming back to the closest equation, we have that radius of curvature times arc length is equal to a squared. From this info about curvature that deals with change rate of tangent direction with respect to time, and so with centripetal acceleration, we will get the velocity vector that is a unitary tangent vector, and from this last vector we will recover the position of points we were looking for. At infinitesimal level, it holds for every curve that the radius of curvature times the angle is the arc length. On the other hand, for a clothoid, this radius times arc length is the constant a squared. From these two equations, one gets a differential equation giving us an expression for the curvature that is for the change of tangent direction or angle with respect to arc length. Starting with this info about the derivative of the angle with respect to arc length, in lesson 5.2, we will recover the functional angle of the variable arc length, applying a process opposite to derivation that is called integration. After that, in lesson 5.3, we will integrate again to finally get the parametric equations expressing coordinates of closely points. Let's see how to use integration to solve differential equations in lesson 5.2.